I want to run you through a problem in Gasp. Before I do that, I want to show you how to run this program using myapps.rush.edu. For those of you who have had trouble running it, this should not cause you a problem. And once again, just bear in mind it is always available in the METC and you can always run it there as well. In order to do myapps.rush.edu, you have to download Citrix Receiver. Just do a search for Citrix Receiver and go and download it. You do not have to put in any login information or anything like that. It requires no setup. Just have it installed. And then you go to myapps.rush.edu and you use your login credentials for Rush, just like you ordinarily would. They're your Outlook credentials. Click on My PC at the top, and then click on My Rush PC. And what will happen is you'll get a Windows desktop that will start up that will look just like you're on a computer at Rush. And if you've never done this before, I recommend that you do this simply because it's a good idea to be able to do it. There's a lot of software that's available through Rush that you'll probably need to use in some of the coming years. And so being able to use this to get into a Rush computer is pretty handy. So this is logging me in. I didn't have to do anything with Citrix or anything like that. It'll just automatically log you in. It's very convenient and quite nice. It does take a few minutes, as you can see here. But once again, I think is fairly worthwhile. Now, I used Google Chrome here, but you can use Firefox, you can use Internet Explorer, you can use Safari, and you can go to Entrada and you can directly download the gasp.jar.zip file, and that's what I did here. And now I'm going to right-click and choose Extract All, and I'm just going to go ahead and extract it right to the desktop. And you can go ahead and just say yes and not worry about this. And now it opens up the folder, and this is your Gasp file, your program file. So I'm going to just double click on this, and that should start up Gasp for us, and we'll be ready to roll. And there it is. This is foolproof. It runs under Windows 7, it runs under Linux, it runs on the Mac. You can do whatever you want. So this is what the program looks like. It should look very familiar to you guys who have done CircSim already. It's a CircSim type prediction table problem. And here is your concept map. I don't use the concept map a whole lot, but some of you, I'm sure, will use it. Students in the past have told me that it's handy. What you are going to want to do is you're going to want to have this equation at the bottom handy, and I'll show you why in a second. So what I'm going to do is I'm going to do the first problem with you. And this is a problem where you decrease inspired O2 to 10%. So it's a decrease in inspired oxygen. I'm going to not run the tutorial, but I certainly do recommend that you do run it. If it's the first time you've used it, it'll walk you through this problem, and I'm going to walk you through it right now. You have an individual breathing room air is switched to a mixture of 10% oxygen. So, as you know, that is less than the normal amount of oxygen. So our initial change is going to be a decrease in arterial oxygen. So I'm just clicking here, and there we have a down arrow, okay? Now, the next thing that's going to cause is a decrease in arterial hemoglobin saturation. So if I go to our hemoglobin saturation curve, you can see if my PO2, my partial pressure of oxygen, which is basically free dissolved oxygen in your plasma, goes down, then the amount bound to hemoglobin goes down. And so we're going to move down this curve. And so that's what I'm doing here. And that will therefore cause a decrease in arterial hemoglobin saturation. That means a decrease in the amount of oxygen bound to hemoglobin. And of course, our total arterial oxygen will go down if both of those parameters go down. Now, the next thing you do is kind of tricky. You have to decide what to do with these parameters for CO2. Now, there's no direct change in CO2 in that we haven't really changed CO2 in terms of the air. We've just reduced the oxygen. So, or we haven't really done anything to alveolar CO2, but what is going to come into effect here is our Bohr and Haldane effects, and those effects are represented by this equation. We present those effects as if they're separate, but they're actually all part of this reaction that you see here: oxygen binding to hemoglobin, and then that having a resulting effect on CO2, or your CO2 changes, and through this series of reactions, it has an effect on oxygen. Now, in this case, we've got less oxygen, and therefore we have less oxygen bound to hemoglobin. What that does is when you decrease oxygen, it shifts all these equations to the right, okay? So we have less oxygen bound to hemoglobin, and what that means is that we have more protons bound to hemoglobin. In other words, if the hemoglobin doesn't have oxygen bound to it, it's going to bind protons instead. So our pH goes up because our protons have gone down here. They're binding to hemoglobin. The equation has been shifted to the right. We've got fewer protons. And so I'm going to go increased arterial pH, okay? So if I have less protons, then this equation is also shifted to the right because I'm going to pull more of a reaction of carbon dioxide with water. And what that's going to do is it's going to result in an increase in bicarbonate. So I'm going to go up with bicarb. And then my CO2 actually doesn't change. And the reason is because that equilibrates with your alveolar CO2. And so you'll convert more CO2 to bicarb, but in the end, all you're going to do is replace that in the air, from the air, which is basically an infinite sink of CO2. So your CO2 doesn't change because everything in your alveoli more or less equilibrates with the air, okay? And with the blood as well. And so your CO2 won't actually drop, your gas CO2 won't. So that's our direct response. We're not going to get a change in ventilation in the direct response. We are going to initiate a reflex response to that. We have decreased oxygen, and that's going to cause an increase in frequency of respiration and an increase in tidal volume. And that means our minute ventilation is going to increase, and that means our alveolar ventilation is going to increase. And if our alveolar ventilation increases, then that tends to bring our arterial oxygen back up, and that means our arterial hemoglobin saturation increases and our total arterial oxygen increases. Now, because we've changed the ventilation, we're changing the alveolar gases. So now my arterial CO2 goes down. And if my CO2 goes down, if we go back to this equation, now this equation is being shifted to the left. So now with less CO2, more bicarb and protons are combining to become water and CO2. And so we've got less bicarb and we've got fewer protons because these are combining to make more of these things because this is being blown off. And so we have a further increase in arterial pH. So now what we do is the same thing we do in CircSim. We add them up. So the easy ones are here, definitely an increase in tidal volume and frequency and in ventilation because we have zeros and ups here. We definitely have an increase in pH, okay? We definitely have a decrease in carbon dioxide, okay? Now the question is what to do with the rest of these. And similar to CircSim, what you do is you go with the direct response unless you have good reason to do otherwise. So we'll go with our O2 will still be down, and our arterial O2 saturation will still be down, and our arterial total blood oxygen will still be down. And that's ordinarily going to be the case. But let's take a look at our CO2. Now this was caused by the reflex response, so it's a nice direct decrease in CO2 gas causing all this. This was caused by our Haldane and Bohr effects. And the Haldane and the Bohr effects in the lungs are very similar to the effect of afterload in the circulation. Remember, afterload is worthless and weak. Of all the things that affect stroke volume, it's the one that really is weak. And so remember with afterload, when it caused an effect in stroke volume, we went with the reflex response instead of the direct response. Well, for oxygen and carbon dioxide, the Haldane effects and the Haldane and Bohr effects are similar to afterload. They're worthless and weak. So if this was caused by the Haldane or the Bohr effect, then you go with the reflex response, because the reflex response is going to be the stronger response. Haldane and Bohr, worthless and weak. So here we're going to go down. And of course, arterial pH is still up because, that was obvious. Okay? So if I click evaluate, this had better work, and it did. So this is the solution to our problem. So that was a typical problem, and here's our solution just with CircSim. And that's how to work it, okay? So good luck. You guys know where to get me. If you're having trouble, just let me know.